actually, I'm talking about something different from what my original.
He's going to talk about finitary coloring.
So my original abstract was basically my open problem from yesterday. I changed my mind and decided to talk about something else in my talk. So apologies for that. Finitary coloring. So this is joint work with Oded Schramm and David Wilson. Because hardly necessary to say with this audience, Oded Schramm was the central figure of his generation in probability theory, probably, and he passed away in a tragic hiking accident in 2008. And David and I took a rather embarrassingly long time to finish this paper, but it is now finished. So what's this all about? Proper colouring of a graph. You all know what this is. You have a graph and you want to label the vertices with some colours, which are just, say, integers 1 up to q, in such a way that adjacent vertices have different colours. So, for instance, if you have z2, then if all you want to do is colour it, then of course you can do it with 2 colours in a checkerboard. So the kind of question I want to think about is, how could we colour with no central authority? I mean, I want to imagine that each vertex is an individual agent somehow, and there's no dictator. It's just a democracy, and they want to come up with a colouring on their own somehow. Okay, so let's try to make that precise. I mean, one thing you could certainly ask for is stationary colorings, so random colorings that are invariant in distribution, translation invariant in distribution. I mean, that's certainly saying somehow the rules are the same everywhere, so that would be a good start. But of course, that's still not a very interesting question yet, because on Z2, if I have 2 colors, there are exactly two colorings, of course. There's the red-blue checkerboard and the blue-red checkerboard. And if you want a stationary coloring, then of course you have to just take that with probability half and that with probability half. But this isn't very satisfying because it has very long-range correlations. I mean, sort of infinitely long. If I know what color this vertex is, then I know the whole coloring.
So what information are they allowed to use?
Well, OK, I'm coming to that. I'm just sort of warming up the motivation, and then I'll be very, very precise in a second. In the other direction, OK, I sort of said I want my vertices to be independent agents somehow. Now, in the extreme case, you could say maybe vertices have IID colors, but of course then you just can't get a proper coloring. There's some color that has positive probability, so you may get 2 neighbors the same. But then you could ask about approximate independence. Can the colors be somehow approximately or asymptotically independent? And of course there are many, many notions, trivial tails, decay of correlations, etc. Many questions you could ask. But I'm going to focus on something very specific. Here's what I want to do. And this is somehow closest to the original, I think, closest to the original thing I said. I want the vertices to behave like independent agents that can communicate with each other, though. So here's the definition. So a process indexed by, let's say, ZD, although you can do it more generally, a process is a finitary factor of an IID process, which I'll abbreviate to FFIID, if, so first of all, you have an IID process indexed by the vertices, UV, indexed by the vertices of ZD, any IID process, and the process I'm interested in, X, is a deterministic function of that, so all the randomness comes from just IID coin flips or whatever at the individual vertices, and the map from U to X is translation equivariant, which it just means it's the same everywhere. So formally it means if you take any translation of, let's focus on ZD. If you take any translation of ZD, then it commutes with the function. So if you were to shift all your coin flips to the right by 1 and apply your rule, again, you would end up with all the x's shifted to the right by 1. Okay, so it's very natural. So it's just saying it's the same rule everywhere. It doesn't treat the origin in a special way or anything like that. And finally, the most interesting part, I want the map to be finitary. So what does that mean? It means if you want to know the color at the origin, say x0, then it's kind of like a stopping time. The rule that determines it is of the form, you look at your IID randomness at the origin looks at its own IID random variable, and then depending on what it sees, maybe it looks at the IID randomness of the neighbours, and then depending on what it sees there, maybe it looks at the next nearest neighbours, and so on. But after some finite but random and perhaps unbounded time, or radius, it knows what colour it should be. Okay, so that's what this says formally, that x0 is determined by the u's on some ball or box. It doesn't matter, I'm not going to care about which metric particularly, for some random radius. And formally that's what it means to be determined. Okay, so that's the definition, and that's what I want to focus on. So the basic question is going to be, does there exist an FFIID colouring? And then if so, we have this quantitative question. We have this coding radius, which is this random distance that you have to look to determine the colour at the origin. How small can we make that random variable? And just to warm up, again, if we're on ZD with two colours, the answer is no, because the only stationary colouring is this two checkerboards with probability half, and it's very easy to see that that's not of this form, so it's not even mixing as a random process. And also you can't do it with R equals 0, because that means you just have IID random variables, and you can't do colouring that way. And I won't dwell on this, but this is very closely related to applications in distributed computing. So you should imagine that you have a network of machines, computers, and distributed computing is all about using networks of machines to solve actual computational problems, global problems, without any central authority somehow. But I mean, this is asking something even simpler. It's just asking them to solve a local problem. It's just asking them to not disagree with each other, to find a proper colouring of themselves. And if you want an actual application of that, you can imagine that the colours represent update schedules or communication frequencies or something for individual computers, and you want neighbours to be not in conflict with each other, so you want a proper colouring. But let's get back to math. So I'm going to focus on ZD. So here's a warm-up example. So you can do this thing. Here's an example of an FFIID 4 colouring of the two-dimensional lattice, Z2, and it's going to have exponential tails of this coding radius. So here's one way you can do that. First of all, so the vertices are going to be squares here. First of all, each vertex just tosses a coin. With probability half, it's black or white. So that gives you some black and white squares. Now, from percolation theory, you know that site percolation on the square lattice, the critical probability is strictly greater than a half. So a half is subcritical. So it means you have black clusters and white clusters, and they are finite. And better than that, they have pretty small diameters. So the diameter of the cluster at 0 has exponentially decaying tails. So now what I'm going to do, of course this is not a proper colouring. If I want a proper colouring, I can checkerboard. I can checkerboard each white cluster in red and blue, say. And I can checkerboard each black cluster in green and yellow, say. And that clearly gives me a 4 colouring. And why is it FFIID? Well, you have to think of it from the point of view of this local rule, right? So I'm sitting at the origin. What do I have to do to determine my colour? Well, I didn't quite tell you how to do this because there are two possible red-blue checkerboards on a white cluster, and I have to decide between them. So one way to do it is just start from the northeast corner of the cluster, the lexicographically largest point in the cluster, and say that guy's red, say. So if I'm the origin and I want to know my colour, what do I have to do? Well, first of all, I have to explore my cluster and find out, I'm in a black or a white cluster, I have to find out what it is, and then I have to telephone the guy in the northeast corner and find out my parity relative to him, and then I know what colour I should be. And how far do I have to look to determine my colour? Well, it's the radius of the cluster, basically, which has exponential tails. Okay. And by the way, one little wrinkle here is this satisfies what I said. It's a translation equivariant function, but somehow I broke some symmetry by saying, look in the northeast corner. So it's not rotation invariant or reflection invariant. So actually, if you want to, you can make it isometry equivariant. And one way to do that is, in addition to these black and white labels, each vertex picks, say, a uniform 0, 1 random variable, and independently. So the randomness consists of the coin flips and the 0, 1 random variables. And then rather than saying that the northeast corner of the cluster determines the parity, I'll say just the largest uniform random variable on the cluster determines it. Look for the largest one. So that's rotation and reflection invariant as well. Okay, so obvious questions are, can we, yeah?
That ladder distribution, how far is that from the uniform distribution on 4 colorings?
Oh, a very long way away, yes, nothing like it. Well, I mean, it depends how you measure, but if you draw a picture of it, it won't look very similar, I don't think.
Okay.
I mean, the clusters, you know, they have exponential tails, but they're not trivially small, I think. You'll be able to tell which is the red-blue and which is the green-yellow, I think. Okay, questions. Can we do better? Can we make, so this was already pretty good in some sense because I only used 4 colors and my R was nice and variable with exponential tails, but maybe R could be bounded. That would be far better. Why not? And of course, what about other dimensions, and what about other numbers of colors? So I mean, more colors makes things easier, but could I do this with 3 colors, for example? Okay, so it turns out on ZD we have pretty much all the answers here, at least in a certain sense, and the answers are quite surprising. So ZD with D greater than or equal to 2. So what about 3 colors? Well, you can do it with 3 colors. So there does exist a FFIAD 3 coloring, and it has a power law tail. The probability the radius is greater than R, probability you have to go further distance than R decays like at least a power law. And you can't do better than a power law. So any FFIAD 3 coloring has infinite second moment of R. And unfortunately, all we can prove is this A is very, very small. It's positive, but very close to 0. So there's actually a big gap between 2 and A. So we don't know what the correct power is. That's a very interesting question. But at least with 3 colors, it's a power law, and you can't do any better than a power law. Okay, so that's 3 colors. What about 4 colors? So I asked, can you do better than an exponential tail? Well, the answer is you can. You can do something quite extraordinary, actually. So there is a 4 coloring with much better than exponential tails. It's a tower function tail. So the probability you have to go greater than distance R is, it's not just doubly exponentially small, it's 1 over a tower of exponentials of height about R. Okay, so that's pretty remarkable. Now, so it's very, very nearly a bounded random variable in some sense. For all practical purposes, it's bounded. So can you do any better? Well, no. Actually, this is tight in the sense that for 4 or more colors, there's a lower bound of the same form, a different constant, which of course makes a big difference with functions like this. Okay, so 3 colors you can do power law. 4 or more colors you can do this remarkable tower function, and that's the best you can do. And again, this was for all dimensions greater than or equal to 2. And 1 dimension is slightly different. In 1 dimension, these constants, depending on D, in 1 dimension, you don't have this power law phase anymore. So of course 2 colors you can't do at all, but already with 3 colors in 1 dimension you can do it with the tower function. Okay, so those are the answers. And I will attempt to at least give you an idea of how these things arise, how these different behaviors arise. Okay, so simplest one to show you is here is how to 3-color Z2. Okay, so And now, for some reason, the vertices are actually the intersections, not the squares. So, okay, if you have a 3 coloring of Z2 and you think about a unit square, then if you think about it for a second, there must be 2 diagonal points that are the same color as each other, because you only have 3 colors. So I'm going to sort of use that fact. So I'm going to, in each unit square, I'm going to draw a diagonal line that way or that way with equal probabilities, and they're going to be IID for coin flips. Okay, if you look at this picture, what do you have? Well, Z2 is bipartite, and if you look at the even sublattice, the green vertices, and you look at the edges that connect them, these green edges, then you simply have critical bond percolation on Z2, but it's Z2 tilted by 45 degrees, because each possible edge, like this one, is either present or absent with probability half. And what about the other edges, the purple ones? Well, they are exactly the planar dual of the percolation configuration, the green percolation configuration. So I have the percolation configuration and it's dual, and it's critical percolation. So the clusters are finite. The green clusters and the purple clusters are finite, but they have power law tails. So what I want to do is assign a color to each cluster. And well, that's good, because these clusters are composed of diagonal lines, so I don't create any, if I color this purple cluster in red, I don't create any color conflicts there. But of course what I have to be careful with is that there's an adjacent cluster, like this green one, and that has to be a different color. And I have to be careful about parity here, because the way I drew it, the odd and even lattices are sort of regarded as different, but I have to treat them the same way. Otherwise, otherwise I might have well have just done a checkerboard to begin with. It doesn't count. Nevertheless, one can do this. So because it's bond percolation and it's dual, each cluster, green or purple, is surrounded by some cluster of the other color, and vice versa. So if you look at the adjacency graph of clusters, so each node here is a cluster in the previous picture, and it's a one-ended tree. So each cluster is just surrounded by some other finite cluster, and you can keep going up as long as you want, but when you go down, the tree is finite. So that's what the tree looks like. So all I have to do is 3-color this tree, and that shouldn't be too hard. I should be able to do that with pretty good tails, because it's a tree and really you only need 2 colors to color it. So here's one way to do it. So first of all, just toss coins, color each node cluster red with probability half. Well, of course that doesn't work, because maybe I have 2 adjacent ones that are both red. But now I delete the reds whose parent is also red. So now at least I don't have 2 adjacent red clusters. And then I'm just going to fill in layers. So below a red, I have a layer of blue and a layer of green alternating until I run into some more reds, and then I start again. I mean, there are many ways to do it, but this will do. And considered on this tree, this somehow has very good tails, because all I need to do if I want to know my color is I need to go up to my first red parent, and that's a geometric random variable. It has exponential tails, so it's sort of very local somehow. So that shouldn't, intuitively, that shouldn't really hurt my power law tails that I already have on the size of clusters. And if you want to make that rigorous, you have to work a bit more, but you can do it with Russo-Seymour-Welsh technology from percolation, and you get a power law bound. But unfortunately, the power is horribly small, as always using this method. Okay, so that's that. And I said, actually, we can do this in any dimension, so we can 3-color ZD with power law tails. And the idea is, and this is much, much harder, or at least the way we did it, it was much, much harder. But the idea is you start with a hierarchical partition of ZD that somehow has the same tree structure as the graph of clusters. And we construct this by some rather messy business with random seeds and drawing balls around them and growing things. The cells of the partition are no longer these things composed of diagonal lines. The cells are actual solid lumps, so I can't assign a single color to each solid lump, because that wouldn't be a coloring. But what I can do is assign a checkerboard coloring using 2 out of the 3 colors to each cell. And if you think about it, there are 6 possible checkerboard colorings using 2 out of the 3 colors. And certain pairs of them are allowed to be next to each other. If I have a region colored like this, then it's okay to have a region next to it colored like this, because the greens are in the same place. So I have to assign a checkerboard to each cell in such a way that they respect this graph. And, well, you can do it. I mean, again, the structure of the cells is a tree, so it's a similar sort of method. Each define these special cells sort of as before, and then each special cell thinks of its favorite checkerboard and it tries to force its descendants to use it. So this is some sort of archduke, and this is his favorite pattern, so he really wants all his subordinates to use it, but he has a problem. He may not be allowed to use it because there's a king and an emperor and so on above him, so maybe he's forced to use this, but he's going to make damn sure that everyone lower down uses it, except that he has to work to it. He has to move along the graph of possible checkerboards until he can reach that one, and then when you get to another special vertex, that gets to take over the task. So anyway, you can do this. Okay, so that was 3 coloring Z2 with power law tails. So why can I do no better than power law tails? Well, so here is. So I'm going to prove, or at least describe the proof, that in any 3 coloring on Z2 in 2 dimensions, the coding radius has to have infinite second moment. And in fact, it's enough to prove this in 2 dimensions, because suppose you had a very good 3 coloring in 3 dimensions. Well, with coding radius that's much smaller, I can restrict it to the plane, so then I have a coloring of Z2, and that is actually an FFIID coloring on the plane, because everything comes from these IID random variables that's underlying everything, and I can think of the whole infinite column of IID random variables that goes through the origin as a single one that's located at the origin. So then I have a really good FFIID coloring on the plane as well. So it's enough to do 2 dimensions. And in fact, there's something much stronger that's true. So any stationary 3 coloring has slowly decaying correlations in some sense, and it's a power law that gives you this if you translate it to the question I'm asking. And the reason is that there's a height function for colorings, three colorings in Z2 specifically. And the height, what that means is, here is a proper 3 coloring of Z2. You think of the colors as 0, 1, 2, and the height function is an integer valued function such that neighbors differ by exactly 1, plus or minus 1, either way, and it's equal to the color mod 3. Okay, so it turns out you can do this to check there is such a thing. You really just have to check that it works out around a unit square. And the height function is determined by the coloring, except that you have to choose the height at the origin. You have that one free choice. Other than that, it's determined. And the point is that the height change around any contour, think of a large contour, must be 0. And that's a problem, because it's a problem if you want to do coloring in a very efficient way with a small coding radius, because it's sort of a global constraint. So the proof is based on that. And I won't go into all the details, but you take a large contour, a very weak condition, just tail triviality of the measure, tells you that the variance of the change in height along a side of the square of the contour is large, and it comes from this lemma, which is quite an interesting lemma. So for hardcore random processors people, I'd be interested if you've ever seen anything like this before. It's sort of various ways to prove it, but I don't know whether it's just an easy consequence of something that's well known. We weren't able to find that. Anyway, if you have an FFIID coloring, or if you have any process with fast decay of correlations, then the idea is that you expect changes along different sides of this large square to be roughly independent of each other. So it means if you just go around the cycle, you shouldn't expect the height to join up when you get to the beginning, and that would be a problem. So that's the idea. Okay, so what about this? So that was, yeah.
With non-deterministic, so just the periodic thing, which is uniform translate of a periodic thing, you don't.
Okay, you're talking about this lemma. So let's just see what it is. So it says if you have any stationary sequence plus or minus one random right tail trivial and not deterministic. Yeah, it's every condition here is important. Since we've got this far, then you look at the sum of these variables from 1 to n, and the variance of that.
How small can it? Do you have some bound, and how fast can it go?
Really, no. I mean, it would be very interesting to just understand this lemma more, and what's the strongest you can say. I mean, I don't even know whether you can say limit instead of lim sup, I think. Yes. No, it's not, actually. No, it's not. No, almost surely. Sorry, it's just the variance. Yeah. Yeah, I'd be very interested to come back to that. Anyone who's interested. All right, so that was the three-coloring power law story. Now let's go to the other, the even more surprising sounding story, the four colors and tower functions. And I'll do the positive direction first. I'll show that you can achieve these tower functions. So the sort of key element that's behind it is something that is known in the distributed computing literature, in fact. So the earliest I know is a paper by Cole and Vishkin in '86 that does something like this, the key ingredient that I need. So what's the idea? I'm going to show you a reduction from, and this is going to be on Z for the time being, just on the line. I'm going to show you a reduction from labeling just means a colouring, except it need not be a proper colouring. A labeling with 2 to the n colours to far fewer. And this is how it goes. So you have just a sequence of integers, but you think of them as an attempt at a colouring of Z that doesn't quite work because maybe there are 2 5s next to each other. You write each number in binary, okay, and then you do the following. You look at pairs, adjacent pairs, and you go down and find the first place where the 2 bits are different, going down. And so you write down the row that you had to go to find 2 things that are different, and also which way round they were. This was 1 0, so I write greater than. And then I do the same thing to these 2. So very, very strange thing to do, apparently. But what it does is, certainly I reduce the number of symbols from 2 to the n to about 2n. And yeah, there's one thing I didn't tell you. If the 2 things are the same, then I just have to have another symbol for that. I just write a star. If the 2 symbols up here were the same, I just write a star. So it very much reduces the alphabet size, but it's no worse at being a colouring. So I get a colour clash on the bottom. In other words, I get 2 things next to each other that are equal, only where I had a colour clash above. Because somewhere else, if these 3 things are all different, then I don't write any stars down here. If those 2 were the same, it would mean that it was that both times the digits differed in the second row, say, and they were both 1 0, 1 0, and that can't happen because this would have to be both 1 and 0. Okay, so very, very strange, but that's the property it has. So now the idea is, so start with just random symbols up here, but with a huge alphabet, 1 billion symbols or something, and then do this reduction. So now I have only 1,000 symbols, and still my probability of a colour clash is no bigger than it was before, so it's 1 in 1 billion. And then I can do it again. I can do it k times, and then I hugely reduce the number of colours. On the other hand, what does this have to do with FFIID? Well, I started with an IID sequence, so if I do this k times, to get this process, I only look at my two neighbours. So if I do it k times, I've only looked to distance k. So if you do this k times, you get something with bounded r. It's just a block factor of an IID process with just some fixed number of colours, 6 plus 1, because if n is small enough, then that's not bigger than that anymore, so you have to stop somewhere. And you get, it's very nearly a colouring. The probability of a colour clash is something tiny involving a tower function. And then the idea of what you do then is you somehow have to stitch together these almost colorings for different values of k. I mean, sort of the idea is you have this process that just very occasionally it makes a mistake. It has two colors the same by looking to distance k. So when I see that, I want to look one further. I want to look to distance k plus 1, and then I'll be even less likely to have a color clash. So by doing this, you can get an FFIAD 6 coloring of the integers. Perfect 6 coloring, and for instance then you can easily get 6 to the d colors on ZD by taking products. You do this on every row and column and take a product of them. So that's rather a lot of colors, but at least it's FFIAD. So now you can reduce the number of colors at least to degree plus 1 by an elimination trick. So here's 6 colors on Z. Wherever I see color 6, I'm going to delete it and replace it with something else. And what I replace it with is the smallest color that's not one of its two neighbors. Okay, so then I get rid of all the 6s at the expense of just everyone having to look maybe one further out. So that's quite good news. And I can keep on doing that until I have 3 colors, or in general, for a general graph, the degree plus 1. Because I have 2 neighbors, so I might need 3 colors to do this. And then, right, so that already tells you on Z you can 3 color with the tower function, which is one of the things I claimed. And on Z2 it tells you can do it with 5 colors. And I claimed you can do it with 4 colors. So then there's another, really rather technical proof where we managed to reduce all the way down to 4 colors in ZD. And it goes via all sorts of reductions, long-range colorings, maximal independent sets. So for this problem, coloring is somehow the same as maximal independent sets. They're sort of equivalent. You can go both ways between them. So we managed to get a 2 labeling with bounded clusters. So black and white clusters, and each cluster just has size at most 100, literally, or something like that. And then you checkerboard the clusters, just like I did at the beginning. And somehow it's very complicated, but it all comes down to the fact that in ZD you can have 2 regions meeting at a corner without actually touching each other. That's somehow what it all comes down to. Okay, what about the lower bound? So I claimed you can't do better than this tower function, which is a pretty remarkable sounding claim. So this is a beautiful lemma. It's one of these things where it's a little bit difficult to know exactly whom to attribute it to. So there's something, again, in the distributed computing literature. There's a paper by Moni Noor in '91 that proves essentially this. You can argue it's really a version of Ramsey's theorem. It's a probabilistic variant of Ramsey's theorem. In any case, whoever's it is, it's a lovely lemma. So it says, it's a completely clean slate here. You can start again. If you have any IID random variables, UI, and you have a function from R real arguments to a finite space, just integers 1 up to q, say, and you look at f of u1 up to ur, and you look at f of slide along by 1, u2 up to ur plus 1, and you ask whether those two things are equal. Then the claim is with positive probability they're equal, and it's not obvious that it's with positive probability at all, but for this I want the bound as well. So not only is the probability positive, but it's bounded below by something which is incredibly small but positive. It's a tower of height about r, and you have a q at the top. And this is essentially tight by the construction I showed you earlier. I'll at least outline how you might prove this. I'll just prove that it's positive. I won't bother with proving the tower function. So It's by induction on R. R is the length of the block. R equals 1 is easy, because then you just have f of u1 equals f of u2, and these are IID, discrete random variables. So R greater than or equal to 2. Here's the key step. It's going to be by induction, and here's the key thing that you do. Here's a set-valued function of r minus 1 arguments. I look at, so here are my r minus 1 arguments. I look at f. I plug in those r minus 1 numbers that you gave me, and then I let the last argument of f be random, just with the distribution that these things are supposed to have. That gives me, this f is now random. And I look at the values it can take. The values it can take are 1 up to q, but maybe it doesn't take them all with positive probability. I look at the set of ones that it can take, a set of colours that it can be with positive probability. That's a set. It's a set that's a function of u, little u1 up to little u r minus 1. And of course, it takes at most 2 to the q values, because it's a subset of 1 up to q. So I apply the inductive hypothesis to that. And the inductive hypothesis says with positive probability, S of u1 up to ur minus 1, where these things are random again now, equals, slide the window along by 1. And then, okay, so that means there's some particular set such that with positive probability they're both equal to that. But what was S? Well, it's this set of values that f can take with positive probability. So f of u1 up to ur is in this set. And in particular, that you can pick a deterministic element of that set, so that with everything here is still true with positive probability, f equals that as well. And now I haven't looked at ur plus 1 yet, and by definition, every element of this set A, which equals this S, has a positive chance of being hit by f of u2 up to ur plus 1, including this A. So with positive probability, this equals that. And that's the induction. And if you believed that, then you could sort of see where the tower function might come from if I tried to make it quantitative, because when I reduced r by 1, I went from q colours to 2 to the q colours. So if I do this r times. Right, and so, and why does that mean you can't beat this tower function for FFIID? Well, suppose you have an extraordinarily good rule for colouring on Z, say. Just look at the places where you didn't have to look further than distance k to determine your colour. Just look at those colours. So you'll get something, if your R is extraordinarily good, better than this tower function, then you'll get something that's almost a colouring. Your probability of a colour clash will be phenomenally small, even smaller than 1 over tower, and this lemma tells you that that's impossible. Okay, so how long do I have? 5 minutes? 2 minutes, okay. So very, very quickly, so just 2 other directions that you can go, both of which are very interesting. You can look at shifts of finite type. So colouring is a local constraint, but you can look at general hard local constraints. And the term here is a shift of finite type. So a shift of finite type just means you have a finite number of colours on ZD, say, but I tell you on 10 by 10 boxes, there are only this atlas of local patterns that you're allowed to have. So colouring is an example of a thing like that, but you can have all sorts of others, just a system of local constraints. So in 1 dimension, we know what happens with any local constraint. There are 2 trivial cases. One trivial case is some constant sequence is allowed, and that's boring. Then you don't need any randomness at all. And the other trivial-ish case is where you have some kind of periodicity, like with 2 colouring, and then you can't do it at all. You can't even have a mixing process that satisfies it. And if otherwise, the answer is it's a tower function. Tower function upper and lower bounds. So this tower function is kind of universal in 1 dimension. In higher dimensions, we don't know. You can have shifts of finite type in higher dimensions, and we have these 4 cases, the 2 trivial ones, and then we have power law cases like 3 colouring, we have tower function cases like 4 colouring, and I don't know whether any of these 3 gaps, I mean, sort of here is where we're most used to working most of our lives. Is there any shift of finite type where the best you can do is exponential tails? So I don't know whether any of those 3 gaps contain anything else. So finally, in 30 seconds, there's another very, very interesting direction you can go. So if you have an FFIID process where the coding radius is bounded, then that's something much simpler. That's a block factor. That says you have IID random variables, and think about one dimension for now, and you just have a fixed length of block, and the color at the origin just depends on this block of k things. Okay, that's a block factor. So the theorem tells you in particular there are no block factor colorings on Z, because you have to have at least this tower function tail. You certainly can't have R bounded. Now, there's another definition, though. A stationary process is k-dependent if things at distance k are independent of each other. So everything to the left of the origin is independent of everything to the right of k. Okay, so k block factor implies k dependent. Maybe it's k minus 1 dependent or something. And this was an open question for quite a long time. Does the converse implication hold here? Are there any processes, stationary processes, that are k dependent and do not arise as block factors? So it was sort of open for about 30 years, but then people found counterexamples, and sort of all the counterexamples people found were quite strange, and they have the feeling of things specifically constructed as counterexamples. So it's a sort of long-standing question is, are there any natural processes, or is it really, for all processes that really arise in practice, these two are equal? Well, it turns out that colouring provides a very nice answer to this. So there's no block factor colouring of Z, but it turns out there is a k-dependent colouring of Z. In fact, there's a 1-dependent 4-colouring of Z, a stationary 1-dependent 4-colouring. This is very surprising and a very, very strange process. And there's no 1-dependent 3-colouring, and there is a 2-dependent 3-colouring. And this is joint work with Tom Liggett. So I should stop here.
Questions?
So maybe a key question is, what's the largest density of an independent set that you can build in this way on Z2?
Yes, this is...
Certainly achieve half of the bond percolation threshold, and a little bit more, since a lot of the clusters have slightly more, black sites than white sites or something.
Right.
And this is a bit bigger than a quarter, so it's a bit better than one of the color classes of the of a 4-coloring.
Right.
So do you think would it be interesting to try to prove upper and lower bounds on?
Yeah, I think. And you get to play with the coding radius as well, of course. That would be with exponential tails. Oh, with exponential tails. Yeah. That's an interesting question. I haven't thought specifically about that, but yeah. So it's a very interesting.
You could use your 3 colorings to get a third.
That's right. Actually, thinking about it, I guess you can. Yeah, I'm sorry. Having thought about it for 30 seconds, I think, at least on ZD, even with tower function tails, you can get arbitrarily close, I think, to the maximum, because once you have a 4-coloring, you can do an awful lot just locally with block factors. So you can sort of divide into big grains and just do exactly what you want in the middle of each one, and then around the boundary you'll lose something. So I think, see, that particular question, I think I know the answer to. But it's a very interesting direction, and there are questions like this on trees and on deregular graphs with slightly different definition of locality that have been looked at and are very interesting.
So it's maybe a related question. If instead of asking for it to be finite tree with a given decay of the radius, you ask for it to be approximable, so you say that it's a measurable function, and you can get it to within probability PR by looking at a radius besides R. Are those two notions related?
Yes, but quite how? I'm not sure.
Then that sort of turns into it, because Andrea, I think, was talking about local approximations of.
Right. Yeah, I mean these things are all very closely related, but slightly different, I think.
Well, one more question to finish us. About the number of colour clashes, if the density is low. I mean, it's almost the same as the
Density.
So you don't have to have a proper colouring.
Uh-huh.
But somehow, in some sense,
So you're allowed occasional errors?
the occasional
Yeah, so that sort of, I mean, depending on exactly what question you ask, then there's a version that sort of comes down to the same thing, more or less, because if you take one of these FFIID things and then say, okay, if my radius turns out to be bigger than 1,000, I'll just forget it and put anything there, then you will get, so at least if you ask the question in that way, then it's sort of the same. Although it's a bit, I mean, I guess it's a bit harder, at least from the point of view of practically proving things, it's a bit harder to actually construct an FFIID process where it works simultaneously for all radii, but sort of morally it's...
Thank you, Ian.